Welcome to a paper on causal feature alignment. I'm Rahul, and the co-authors on my paper are Parag, Vikram, and Professor Ambedkar. We will be discussing about our method on reducing the problem of spurious feature and thereby increase the worst group accuracy. It's well known that classically trained ERM algorithms are susceptible to failures arising out of dependence on spurious features. The spurious features can occur in the form of background or color or the presence of a device logo, etc. This decrease in performance can be observed accurately in the case of domain generalization and while evaluating works group performance. Group corresponds to sets of data with shared characteristics. For example, to the right contains two types of birds, waterbirds and landbirds. Now, waterbirds can occur either on land or water, forming two groups, while landbirds can occur on land or water, forming an additional two groups, resulting in a total of four groups in this data set. The accuracy on each of the groups is evaluated, and the worst accuracy is called as the worst group performance. This has implications on the fairness of the algorithm. Researchers have studied this algorithm in fair detail, and the gold standard algorithm on this problem is myriad, which requires access to the group from which each sample is drawn from, and the weight of each sample in the ERM training is weighed according to the inverse of the number of samples in the corresponding group. To overcome this, a number of algorithms have been proposed that reduces the requirement of group labels for all samples in the training data set. A prominent algorithm in this set is feature reweighting, where the authors have observed that while the feature representation network outputs features from both the spurious as well as the causal features, the classifier ignores the causal features, resulting in reliance on the spurious features. They try to alleviate the problem of the classifier by retraining only the classifier on an equally balanced dataset. However, there are a couple of issues on the prior methods. Number one is these methods require knowledge of the groups before the training step, which is extremely hard to obtain in practice. Number two, constructing equally balanced dataset, even on validation dataset, is extremely hard because of the occurrence of samples from the minority group. For example, if the occurrence of samples from minority group is less than 5%, to obtain even 50 samples would require access to 1,000 samples in total. Finally, all the methods described in literature work in the scenario where the spurious attribute is limited to only one and does not scale in practice. We take a slightly different approach to the problem and limit our problem to the scenario where the spurious attribute can be spatially delimited. An example of such a manifestation is where the spurious feature is a pattern. Let's observe the schematic here. Each image is composed of the background as well as the causal feature, and the neural network observes X, Y. We represent the neural network as a combination of feature representer followed by classifier. In the ERM training, it is observed that the classifier ignores the features that are derived from XC while relying on features from XP. In our algorithm CFA, we rebias the feature representation learning to utilize features from X, C, and limit the use of XP. In our method, first step is simply ERM training. The second step, for a subset of data, we obtain the segmentation mask through the use of a foundational model. In the third step, we force the representation part of the neural network to utilize only the causal or the foreground or the features that copy label. That is predominantly achieved through the use of an alignment loss. In the alignment loss, 5 ERM takes as input XC, which is obtained as an element-wise multiplication of X and 1, and 5M, phi of X is minimized with respect to the features obtained from only the causal part of the image. To ensure that the obtained features are also meaningful for the task, we continue to train along with the classification errors. We demonstrate our algorithm on the color in this dataset, where the background consists of the color and so the Spurious feature. We see that in ERM, the algorithm obtains impressive performance in domain by performing suboptimally in the out-of-domain scenario of 59%. FRR is the state-of-the-art algorithm with 64.9%, while our algorithm improves to 99% even on out-of-domain. A caveat here is that FRR does not require any additional human input, but we require access to subset of a small set of datasets. We also observe that our network relies very little on the color features from 0.81 in ERM to only 0.19. We proceed to demonstrate our experiments on benchmark Waterbirds dataset. The Waterbirds dataset, there are 4 groups with G2 and G3 being the minority group. We observe that our worst group accuracy outperforms all the previous methods. But more importantly, we also constructed a new test set where the backgrounds were not seen in or backgrounds of that class were not seen in the validation or the training data set. While our algorithm retains the same performance as before, algorithms like DFR, DTT, and SubG do not perform at the same level. Thus, in conclusion, we demonstrate a method that is much simpler than previous methods when the problems can be limited to the spurious features appearing in the form of background. This allows us to work on problems where the groups cannot be specified beforehand. We also reduce the sample complexity of obtaining a large number of samples from the minority group. Thank you.